Hello again and welcome back. CP2c Mass and weight, in my opinion, the most crucial topic in CP2 because people often get confused between mass and weight. Would you look here? Another formula triangle, the most beautiful thing ever created by mankind. Let's do this. Okay, so we've got weight on the top in capital W, and weight is measured in kilograms. Oh, sorry, no, weight is in newtons. Okay, weight is in newtons. Crucial to know. Let's put brackets there. Newtons. Made that mistake myself, actually, so note that down. Weight is in newtons. Up down here, you've got mass. That's a lowercase m, which is measured in kilograms, or grams or kilograms, obviously. Just the metric system. And finally over here you've got the most important one, gravitational field strength. For combined science, I'm not sure you even need it with separate sciences, but for the case of combined science, 10 newtons per kilogram is the gravitational field strength on Earth. So we just put G there for gravity in newtons per kilogram. So that's 10 for Earth. And there's our formula triangle done. So, right, what else? What else do we need to know? Ah, okay, yeah. Let's look at this. Did you know? Gravity is not the same everywhere on Earth. Your weight is greater standing at the North Pole than it would be standing at the equator. I think that's because Earth is not really a sphere, it's a distended sphere. So the poles are closer to the core of the Earth than the equator is. So your weight would be greater at the North Pole. Right, let's look at these worked examples. What's the weight of a 90 kilogram astronaut on the surface of the Earth? Okay, if we're looking for weight, we've got to cover up weight, and we go for mass and newtons per kilogram. And this is where what I told you before comes in handy, because it says the surface of the Earth. The gravitational field strength on the surface of the Earth is 10 newtons, so we can do 90 kilograms multiplied by the gravitational field strength of the Earth, which is 10. So we've got 90 kilograms, 10 newtons per kilogram, and that equals 900. So the weight of the astronaut on Earth is 900 newtons. This one. A space probe has a weight of 3,000 newtons on Earth. What is its mass? Mass is weight divided by gravitational field strength. So let's take the weight, which is 3,000, and divide it by the gravitational field strength, which is 10. So 3,000 divided by 10 is 300. So 300 kilograms is our weight. So the satellite probe has the weight of 300 kilograms, which, as you can see there, is also the answer. 900, 300, 900, 300. Good. Okay. Oh yes, this is a good one as well. There's so many questions that I'm missing out on. A 300 kilogram space probe lands on Titan, where the gravitational field strength is 1.4 newtons per kilogram. What's its mass on Titan? Explain your answer. So we can say, to find the mass, we need to do weight divided by grams in newtons. Weight divided by gravity. So the weight is 300. So we do 300 divided by 1.4. Yeah, divided by 1.4. Yes. Okay. And if I bring up calculator again, we can see that 300 divided by 1.4 equals 214.28. We should always go to, if it doesn't specify the decimals, go to 2 decimal points. So we can say equals 214.28. 214.28. 8. And because we're finding mass is in kilograms, so the mass is 214.28 kilograms. Explain your answer. This is the mass because, I suppose you'd say the mass is not 30 kilograms because the gravitational field strength is different to 10 on Earth. What's its weight on Titan? So if it's 300 kilograms on Earth and it's 1.4 newtons per kilogram, let's see. Right, what's its weight on Titan? So we take the mass when it's on Titan, which goes here, and multiply it by the grams and newtons per kilogram. This should give us, I imagine this should give us 300 kilograms again, which is almost definitely not the answer. So if we take 214.28, or it will be roughly 200 because I didn't go through all the decimal points, times by 1.4. Yeah, that's how you do it. Weight, mass times. Yeah. Yeah, that's how you do it. Yeah, no mistakes here. Wait. So that's where I've made a mistake. Yes. Ignore this. This is incorrect. If I just redo this. Ignore this. The actual thing would be, because 300 kilograms is in mass. So to find the mass on Titan, you would, if it's 300 kilograms on Earth, you'd find, okay, weight, okay, mass is, okay, yes, okay. Mass is universal, which means that this is a trick question. The mass on Titan is still 300 kilograms. Sorry. Kilograms. It's not 214 kilograms. It's not that. 300 kilograms, because kilograms, mass is universal. So if it's 300 kilograms on Earth, it's going to be 300 kilograms on Titan. So we can then go forward to find the weight. The weight on Titan, which is what I think I was working out before. Weight equals mass times gravitational field strength, which is still not this. So ignore this again. Mass 300 kilograms multiplied by 1.4. There was no calculator needed for that first question. Then again, open up calculator, and 300 times by 1.4, sorry. And that gives us 420. So if I just go back to here, equals 420. So 420 newtons is our answer. So the answer to that, weight on Titan is 420 newtons. Finally, 4 marks. This is going to be interesting. But, okay. The mass of a spanner on Earth is 0.2 kilograms, and its weight is 2 newtons. The spanner is taken to the moon as part of the astronaut's toolkit. Compare the mass and weight of the spanner on the moon and on Earth. Were we given the gravitational field strength on the moon? Or do we just have to just say that the moon is less gravitational force than the Earth? Compare the mass and weight of the spanner on the moon and on Earth. So yeah, okay, we're saying that because the gravitational, I'm just going to say gravity, because the gravity is less on the moon, and and mass is universal, mass would remain the same, but weight would decrease on the moon due to the I will just enter there. Due to the lower gravity. And that gravity, full stop. And that is our 4 marks, I believe so. If we need to refer to units, I'll do that now. Mass would be 0.2 kg on moon and earth. Weight would be... I think we're going to have to calculate this, aren't we? The weight is 2 newtons. Oh no, we're not going to have to, because we just say weight would be less than 2 newtons. Because if it hasn't given us the gravitational field strength of the moon, we don't have to work it out. So let's see if we can get 4 marks from this. Gravity is less on the moon, I think that's 1 mark. Mass is universal, that's the 2nd mark. Mass would remain the same, weight would decrease, that is definitely 4 marks. So that's our 4 mark question. CP2c Mass and weight. I think this is... yeah, before we wrap it up, I will just go over this, see what it's about. Falling object has force and air resistance on it as well. Yeah, so as the speed goes up, the drag and air resistance also goes up, I suppose. Yeah. Alright. I think we might come back to that, but ignore whatever I just said for a minute. This is all you need to know. Lovely formula triangle, mass and weight. I will see you in the next one.